Okay, so my name is Adrian. I've worked for ADI as a software developer for the past almost 4 years. And I'm going to show you how you can build a radio with M2K and spare parts. So before we begin, I'd like to talk a little bit about the Analog Devices Active Learning Program. So it is dedicated to inspiring students to better understand the world of electronics and analog signals, and it tries to bring technology into the classroom. So the active learning program consists of boards. So we have these boards that are called active learning modules. There's the M1K, add-on 1000, add-on 2000, which we call the M2K, and the Pluto, which is an SDR. So we also provide free courseware, lab materials, and free books for teachers to use in their courses. So the hardware is the M2K, which is an affordable USB-powered multifunction instrument. So this is not the Pluto, but it's based on the same infrastructure as the Pluto. So it has a Zinc Z7010 SoC that is running Linux, but it has a different analog front end and it has the AD9963 chip. But the connectivity options are the same as the Pluto, so you can connect to it using USB. You can have a Wi-Fi dongle or a LAN dongle, or you can put in even a memory stick. If you want to use the OTG capabilities of the Pluto, you would also need to use the secondary power connector. So it's all open source hardware, open source software. You can check out the source code, the schematics at the links there. So, like I said, it's based on the same infrastructure as the Pluto. So the bottom part is pretty much the same. You have USB 2.0, you have libIO, there's Linux running on it, but the analog front end is a little different. So what are the specs of the M2K? So it has a two-channel 100 megasamples per second ADC with an input range of plus minus 20 volts. It has 16 digital input-output channels at 100 megasamples per second. It has a trigger mechanism which supports both internal and external triggering. Has a two-channel DAC which is synchronized at 150 megasamples per second. And it also has a plus minus 5 volt power supply. So how you can interact with it? Well, there's Scopy, which is our GUI software. There's the libm2k, which is a C++ library. You can use a GPIO out of 3 module. And there's also the M2K CLI, which are a set of command line tools. So in order to better understand what's going on, we have to look at the analog signal chain. So like I said, the M2K is an embedded Linux host. It gathers data from the hardware, puts it into the kernel, and eventually uses the IO subsystem to manage all of the inputs and outputs. There's an application which is called IOD that's a daemon that's running on the M2K, which helps send the data over the USB or Wi-Fi link back to the host computer. So on the other side of things, once the data reaches the host computer, you can use libIO to get the data. And from this point, you can do pretty much anything that you want with the data. So in our case, we use the libm2k, then GPIO, and eventually GNU Radio to do some of the signal processing. So the software, it's called Scopy. It is a touch-friendly, modern-looking software. It leverages GNU Radio to implement a bunch of virtual instruments, such as the oscilloscope, the signal generator, voltmeter, power supply, spectrum analyzer, network analyzer, and a bunch of logical instruments as well. So this software is also open source, and it's still under active development. Also, I'll quickly mention the M2K CLI, which are a set of command line tools for the M2K. They can be used for calibration, configuration of the device. So there is no need to write extra software if you want to do just something basic with the device. You can power up a bash console and just create a script to automate your measurement and configuration. The library, it's called the libm2k. It is a C++ library to interface with the M2K. So in IIO, there are lots of switches and knobs that need to be like in the perfect order for things to work. But what libm2k does is that it abstracts all the device initialization, calibration, and operation in easy-to-use methods. So it is built on top of libIO, and it has a minimal set of dependencies. But and we also provide build instructions for Windows, Linux, and Mac OS. There's also a Windows installer because building things on Windows can be hard. So you just run a setup and you're good to go on Windows. We also created Python bindings, C# bindings, and MATLAB bindings for the libm2k. And it's all open source with LGPL license. So earlier today, you caught Travis's, maybe you caught Travis's lightning talk about our different transceivers. So there was a slide about different kinds of radio architecture. There's the superhead in the top left. There's the direct RF, which is on the top right. And then there's the zero IF on the bottom. So what we're trying to do here is kind of create this kind of zero IF transceiver where we get the data from the antenna, we amplify it, down convert it with the mixer, and then use the M2K to do the digital signal processing. So how do you build a radio with the M2K? So in the top left, there's the experiment, let's say. It has like, it gets data from the antenna. It's exactly like in the previous slide. It gets amplified, down converted by the mixer, and then sent back to the M2K. So all of the parts used are commercial off the shelf. We got the parts from eBay and from eBay and Amazon, and it was super cheap to build. So here on the right, there's the diagram of the M2K, the diagram of the radio, and we use the AD83831 mixer to down convert, and we use the ADF4351 PLL to provide the LO frequency. The problem is, though, that the ADF4351 is digital. It has a digital configuration interface, so you would need some kind of other hardware to be able to interface with it. So maybe you would need something like an Arduino with a knob, or maybe a Raspberry Pi, or I don't know, maybe you could rewrite the M2K firmware to be able to handle that. But that seems like a lot of extra work. So we're going to show you how we use the libm2k to configure the PLL. Also, if you really want to achieve performance, there are all of those filters which are not in place in our prototype. But if you want to achieve good performance, you would have to design those filters as well. So I just want to show you here like what the libm2k is. It is used to make interacting with the M2K easier. So I'm going to show you some of the features of the libm2k and how you can use them in different radio systems. So in order to access the M2K, you would have to create a context. So you would create a context using the M2K open function, and then from this context you would get handles to all of the different all of the different instruments that the M2K provides. M2K contexts, like I said, are basically device handles. So M2K contexts handle like device calibration, device initialization, identification, and then provides handles for the rest of the instruments. Multiple devices can be instantiated with the libm2k, and so you can do synchronous measurements across multiple devices. So on the right, it's a simple Python example of how like a hello world for the libm2k. You just open the M2K, calibrate the ADC, you get the handle for the analog input, and then you just get the voltage. It's super easy to use. So the analog in class is the interface to the 2-channel 12-bit 100 megasamples per second analog input. This analog input works at baseband. So like I said, this is not an RF transceiver. This is more like an instrumentation thing. So this works at baseband. It has an input voltage in low gain of plus minus 25 volts and plus minus 2.5 volts in high gain. And with the libm2k, you don't have to worry about converting from raw values to volts, because all of these methods are provided for you. Also, there's triggering, which I'll show in the next slide. But you know, you can use this analog input in your radio project to get analog data from your system and basically do anything that you want with it. So the hardware trigger class is an interface to M2K's versatile trigger mechanism. So what it is used for is to condition signal acquisition either by edge or by signal amplitude. There are two types of triggers. There's internal triggers and external triggers. So internal triggers rely on the state of the signal for both the analog and the digital interface, while external triggers rely on external trigger pins, such as the trigger input pin, trigger in pin. When you get a signal on that pin, it triggers a measurement. There's also a trigger out pin on the M2K, and what this does is basically whenever the M2K detects a trigger condition, it forwards a pulse on the trigger out pin. So what this is used for is to daisy chain multiple M2Ks in order to do synchronized measurements across multiple devices. So for this project, the analog trigger was not that useful, because in order to get radio, you would have to get all of the signals, all of the data that's coming through. You would not need any signal conditioning, but it is useful. What the digital trigger is useful. So I'll show you immediately how. The analog output is the interface to the M2K's 150 megasamples per second 2-channel synchronized DAC. So similarly to the analog input, it provides easy-to-use methods to push the data to the DAC, convert data from raw to volts, and different other configuration options. So it can be used to provide LO signal for up to 20 megahertz, and or also if you want to build like a radio transmitter, it can provide an intermediate frequency. The power supply and the DMM, so DMM stands for digital multimeter. These classes are the interface to M2K's power supply, which is a plus minus 5 volt, 50 milliamp power supply. We couldn't use this power supply for this project because our power requirements are way bigger, 12 volts, 150 milliamps. But I thought it was worth mentioning. So the picture on the right is actually a screenshot from Scopy. And it kind of shows that you have a 5 volts on the positive output and minus 3 on the negative output. The DMM is an interface to the M2K's internal voltages and temperatures and can be used for the different kinds of device monitoring. The digital interface of the M2K provides 16 digital inputs and outputs which are capable of buffered operation. And also triggered operations. So as outputs, they can be configured either as push-pull and open drain, and so they are ideal to bit bang a variety of protocols, and from the input you can decode, again, a variety of protocols. So in this project, the digital interface was used to configure the ADF 4351 PLL in order to generate LO frequencies. So like I said, the ADF4351 has a SPI interface. I'm sure a lot of you have heard about SPI, Serial Peripheral Interface. It is a protocol that's used to configure a variety of devices. So what we did was we created a SPI encoder and decoder that makes use of M2K's digital interface to better communicate with the devices. So the API that we use is similar to a lot of drivers that we have. I'm going to go over that in a minute. And the cool thing about it is that it runs on the host machine. So it's not on the firmware, it's not on additional hardware, you just run it on the host machine. The NoOS driver repository contains a bunch of ADI drivers for a bunch of ADI components that are not meant to be run on devices that have OSs. So it's like bare metal drivers for microcontrollers or for the user space. And there on the bottom left, you can see the API that it's used. So all of the drivers use the same API. It is SPI init, SPI remove, SPI write and read, which is the same API that we used for the M2K engine. So what you can do is basically take a device driver from the NoOS repository, link it against the M2K SPI engine, and you can communicate with the device. You just compile the program, and you can communicate with the device like straight from your application. You don't need additional hardware. The ADF4351 sync. The ADF4351 is a voltage-controlled oscillator. It has a range from 35 megahertz to 4.4 gigahertz, and it's configurable through SPI. So, like I said, it has an easy-to-use driver in the NoOS repository, and now I'm going to show you how easy it was for us to build the ADF4351 sync, which is a GNU radio block that uses the M2K to interface with this PLL. So first of all, you have to include the driver. Then you create like the boilerplate code for the ADF4350 sync. I think, yeah, you create the boilerplate code for it, like the constructor, the destructor, and everything. Inside the constructor, there are two parts of interest. So the first part is the first part of the structure here, which has 100,000, which is I'm sorry, it's actually 1 million. That refers to megahertz. It's 1 megahertz, which is the clock input, which is the clock sorry. It's the clocking of the SPI interface. Then there's the chip select pin that we use, and the URI. The URI is the actual location of the M2K device. The second part of interest is the one that is underlined here, the ADF4350 setup. This function comes straight from the driver. You just call this function, and the driver handles all of the initialization for you. Then we map whenever you receive a message using the set message handler, whenever you receive a message, we map that to a function, and then we write the actual function to change the frequency whenever we receive the message. So we run this function from the driver, the ADF4350 set frequency, and this is basically it. We get the frequency from the message, and the driver handles all of the SPI transactions between the M2K and the PLL. So this is what the block looks like. Here are all of the registers that you need to set up, and yeah, you're good to go after this. So how it all fits together, we initially, when experimented, we created this board, which has all of the components together. But eventually, we created like a more integrated version, which is more robust, more easy to use, in order to get FM reception. In GNU Radio, we created a Python script to initialize the libm2k. We used the ADF4351 to configure the PLL. And we used the IO device source block in order to get the analog data from the device back into the GNU Radio flow. Then we used a bunch of signal processing blocks to actually demodulate the data and send it back to an audio sync. So here's a demo of how it works. I hope you can hear it because it's not hooked up to the audio of the HDMI. So. Yeah, sorry about this, but it's. Yeah, I'm sorry, but the audio doesn't go through. So, yeah, we definitely have a demo at the booth. So you can see that the FM signals are coming through. Then we tune the frequency, and now you could actually hear the radio that's coming in. So as conclusions and future plans, I said that it is possible to use the M2K's analog front end to capture RF data with proper circuitry, and the M2K is a good combo to get started with electronics and even SDR. So in the future, we plan to extend libm2k's functionality. So we want to create like a out-of-tree module, GRM2K, which is based on GRIO to provide more easy ways to communicate, to interact with the M2K through GNU Radio. We want to create also interfaces for other protocols such as the I2C and the UART for better integration with our drivers. These interfaces, we want to put them into the libm2k, into the M2K CLI, so you can program devices right from the console. And eventually, we also want to add Debian packaging for libm2k and Scopy, so you can install them using apt-get. And yeah, thanks.
Do we have any questions for Adrian? No, because I have one. So I saw in one of your screenshots of Scopy what looked like a Windows 10 program.
Yeah.
And then I went to your GitHub repository, and you have nightly Windows builds.
Yeah, that's true.
So you have nightly builds of GNU Radio in Windows.
I guess
we don't have,
as well.
we don't even have yearly builds of GNU Radio in Windows.
Yeah, we do them. We do them with MSIS.
Yeah, I don't know what that is. We should figure out how to do that, because that would be awesome. It seems like a path forward for GNU Radio support in Windows.
Sure.
Oh. No? All right. Thank you so much, Adrian.
Thanks.